In this lecture, we talk about Poincare duality. So first, let us see the duality between cube and octahedron. So you take a cube and choose the midpoint of every face. So top face midpoint is this. So for this face, midpoint is this. Front face, midpoint is this. Midpoint here, midpoint here, midpoint here. Join them, you get an octahedron. Now you consider octahedron. Take the midpoint of every face. So the face is a triangle. This triangle has midpoint this. This triangle has midpoint this. This is midpoint of a face, midpoint of a face. So we are just taking midpoint of every face. Join them, you get a cube. Now we put both of them in one figure. You see the cube and you see the octahedron. Now what you can do is you can fill air in it. Now if you fill air in it, so you fill air in it, so this will look like an S2. So on S2 you have two structures. You have structure of a cube. This we will denote by C, and you have structure of an octahedron. This we will denote by C star. So the property you can see is that the edge of the cube cuts edge of the octahedron only once. So I'm drawing this edge of the cube in red. So you can see it cuts the edge of the octahedron only once. So let us write this. So you consider both cube and octahedron as cell structures, C and C star on S2. And we have noticed that edge of C and C star cut each other once. So there is one-to-one correspondence between the edges. So C1 star is equal to C1. Second is that each two cell of the cube. So each two cell of the cube. So notice that this is a two cell. It contains a dual vertex of C star. So each face of the cube contains the vertex of the octahedron. So each two cell of cube C contains the dual vertex, that is the vertex of the octahedron. So you can identify each face of the cube with the corresponding vertex. So basically you have this face of the cube, you identify with it this vertex. So you have identified C2 face with the vertex of octahedron. Then you can take each two cell of C star. So now you focus on the octahedron. So this is a two cell of octahedron. So this two cell contains the vertex of the cube. So you can identify this face with this vertex. So you can put them in one-to-one correspondence. So each two cell of C star contains the dual vertex of C. You identify them. C2 star is equal to C0. So what you can do now is compute homology and cohomology. So we already have the cell structure. So let us write them down in a format. So we are going to make things a little bit simpler here. Homology and cohomology is generally computed with these integer summands, and these integer summands take orientation into account, and therefore you have these plus minus signs, and we want to ignore these plus minus signs. So we will drop this integers and instead choose this simpler Z2, and this will help us ignore these plus minus signs. So now coming to computation of homology and cohomology. So first you focus on the map, this partial in homology, which takes each face to the sum of its boundaries. So for example, if you're focusing on this top face, so you apply delta to it. What it will do is, to this face it will apply so to this face this delta operator will assign 4 edges, which are its boundary. So you have this face here, to the face you have 4 edges. Now corresponding to this face you have this dual vertex. So this dual vertex of octahedron I'm drawing in green, and we are now going to say that this map D, this D assigns to a cell all the faces whose boundary it is. So there is one-to-one correspondence anyway between C2 and C0 star. So we are taking this vertex right here. So if I'm taking top face here, I'm taking this vertex is same as this vertex. So to this vertex, so this vertex I'm taking right here now. So to this vertex you assign 4 edges. Those 4 edges are precisely these 4 edges which are coming out of this vertex. So that means that D assigns a cell all the faces whose boundary it is. So this point is the boundary of 4 edges. So 4 edges, these 4 edges, 1, 2, 3 and this 4th edge. So there are 4 edges here. Anyway, we have shown C1 and C1 star are in one-to-one correspondence right here. Finally, to these 4 edges you're going to assign a triangle face. And here to these 4 edges you're going to assign, so to these 4 edges you're going to assign these vertices. So this vertex here for one of the edge is same as this vertex in the face. So these 4 edges will give you 4 faces and 4 vertices. Similarly here these 4 edges will give you 4 corresponding vertices. So I'm just drawing one for the sake of illustration. So there is this one-to-one correspondence. What the map delta does here, the map D does exactly the same, because we have this one-to-one correspondence between the cells and the maps which we have just described here. So whether you do delta or you do D, these maps are the same. So if these maps are the same, if you compute kernel over image for these two maps, it will be the same. But notice that this map is homology. Indexes are decreasing. You're going from C2 to C1 to C0. On the other hand, this map is cohomology. Index is increasing. You're going from C0 to C1 to C2. So notice the dual nature between these two. So here you find kernel over image, you will get homology groups. Here you find kernel over image, you will get cohomology groups. So first you find homology group here, which will be H0. The corresponding here cohomology would be H2. So H0 will be equal to H2. So we are not worrying about orientation, and that's why we can do it. So here you will have H1 and here you will have cohomology. So H1 is equal to this, and here again you will have H0 and here you will have H1. So these two will be equal again. Here you will have H2. So H2 will be equal to H0. So in general you can say this H subscript I, this will be equal to H2 minus I. So there 2 is the dimension of this S2. So Poincare duality in general, what it does is you can write Hi, this is equal to Hn minus I, and the dimension of this M is n. So just like here the dimension was 2, here it is n. So this is what is Poincare duality.